Do you ever stop and think about what's actually happening the moment you start typing into a search bar? You know those suggestions that pop up instantly? That's not magic. It's an incredibly fine-tuned system, and it's designed from the ground up for insane speed and massive, massive scale. Today, we're going to pull back that curtain and design that exact system.
Right? So how does it work? How can a system possibly dig through billions of search terms and give you the perfect suggestions before you even finish typing your thought? That's the big question we're tackling today.
Okay, let's get into it. You've got to understand this is a huge race against three opponents at the same time. There's latency, that's the delay you feel. There's load, the sheer number of people searching at once. And then there's relevance, making sure the suggestions are actually what you want. So let's design the system that can win that race.
First things first, before we even think about servers or databases, we have to know exactly what we're building. We need to define the problem and lay out the rules of the game.
So, what are we actually trying to build? Well, it boils down to these four things. 1. Low latency. It has to feel instant, non-negotiable. 2. High throughput. We're talking about handling a fire hose of traffic, maybe tens of thousands of queries a second. 3. Relevance. We can't just show random words, we need the most popular, most trending stuff first. And 4. Scalability. The system has to be able to grow without falling over.
So to solve that first problem of finding matching words really fast, we need the right tool. And in system design, that often means picking the right data structure. For that, we need to talk about a really cool data structure called a trie.
So what is a tree? You can also call it a prefix tree, which kind of gives away what it does. Think of it like a tree where every path from the very top root down to a node spells out a word or a prefix. It is literally built for the exact problem we're trying to solve.
Okay, let's just walk through an example. Say you type SYSTEM. The search starts at the root, finds the S branch, then the Y branch from there, and so on. When it gets to that final M node, that node is special. It holds the keys to every full search term that starts with system. It's just unbelievably efficient.
Okay, but wait a second. Just finding the words isn't good enough, right? A simple try will give us every possible match. We don't want that. We want the top 5 or top 10, the ones people are actually searching for. So now we need to add another layer, ranking.
Now, even with this super fast trie structure, doing that search and then ranking the results for every single keystroke, well, it's still too slow when millions of people are doing it. To get that truly instant, millisecond level response, we have to talk about caching.
Check out this number, 10 million nanoseconds. That's for a single lookup in main memory. Sounds fast, right? But when you're dealing with millions of requests, all those tiny delays add up into very noticeable lag. We have to be faster. We need a cache.
And this is where caching comes in. It's our secret weapon against lag. The idea is simple, right? If something takes a while to figure out, you just write down the answer somewhere really close and easy to grab so you don't have to do the hard work again and again.
And here's the really clever part. This is the key insight. What if we change our tree? Instead of just having nodes store a character, what if every single node also stored a pre-calculated, ranked list of the top 10 suggestions for its prefix? Then, when a user's search lands on that node, bam, the answer is already there, ready to go.
So, how do we put this into practice? A super common pattern is called cache aside. It's just a simple set of rules. First, the app checks the super fast cache. Is the answer there? Great, we're done. If it's not, we call that a cache miss. Then we do the slow work of going to the database or the full tree. But, and this is crucial, we then save that result back into the cache. That way, the next person who asks for it gets it instantly.
Okay, so we're fast, we're snappy. For one person. But what happens when a flood of millions of users show up at the same time? Now we have to talk about how to handle that flood. Let's talk scale.
Yeah, a single server is just going to fall over. No way it can handle something like, let's say, 48,000 requests every single second at peak. So we have to get smart. We use a few classic tricks of the trade. We use a load balancer to act like a traffic cop, spreading requests out over a bunch of servers. We can replicate our data, so lots of servers can handle read requests at once. Or we can do something called partitioning or sharding, where we actually chop up our trie and put different parts of the alphabet on different machines.
And this is something you always have to remember in system design. Your system is only as strong as its weakest link.
Look at this. If you have one part that's 99.9% reliable and another part that's also 99.9% reliable, but they depend on each other, your total system availability actually drops. It's why building redundancy is so critical.
So we're fast, we're scalable, but our data is kind of stale. It's based on what was popular yesterday or last week. What about what's trending right now? To be really relevant, our system needs to have a real-time pulse. To pull this off without slowing everything down, we have to shift our thinking from synchronous to asynchronous. Think of it like this. Synchronous is like standing in line at the back. You wait, you get served, the next person goes. It works, but if one person has a problem, the whole line stops. Asynchronous is more like dropping off your dry cleaning. You drop it off, get a ticket, and go on with your day. The work happens in the background, completely separate from you.
And the tool that lets us do this is a message queue. You've probably heard of things like Apache Kafka or RabbitMQ. They're the backbone here. Every single search query becomes a tiny message that gets fired into this queue. Then totally separate worker services can just read from that stream of messages, figure out what's trending, and update our trie in the background, all without ever making a user wait.
All right, we've talked about tries for finding prefixes, caching for speed, scaling for the masses, and message queues for real-time trends. Let's put all these puzzle pieces together and look at the final picture.
And here it is, the complete blueprint. Let's trace a request, shall we? You type a letter, it hits our API gateway, gets sent to a load balancer, which picks one of many app servers. That server instantly replies from its cached in-memory trie. Meanwhile, in the background, your search query was also sent to a message queue, where a streaming processor is constantly listening, updating the master database, which then refreshes the tries. It's a beautiful, living system.
And if there's one thing you take away from all of this, it should be this quote. In system design, everything, and I mean everything, is a trade-off. There is no single right answer. We chose speed over some consistency. We chose complexity to get scalability. Every single decision is a balancing act.
So, that's autocomplete. But now I want to leave you with a question. Now that you know the building blocks, the tries, the caches, the message queues, where else do you see this stuff? Think about your newsfeed, your friend suggestions, your product recommendations. These patterns are everywhere, hiding in plain sight, powering our entire digital